I should probably start this. There we go. Now we're recording. So there are two parts to this fundamental theorem, like I said. One is the antiderivative part, and the other is the evaluation part. So we're going to first start with the antiderivative part. And so what we've been talking about with integrals, right? This is our integral sign. What we've been talking about with integrals so far is that basically they just represent the area underneath the curve. True? Everybody good with that's what we've been doing, is that they represent the area under the curve?
Yeah.
Okay. And we did the limit, we did the summation to figure that out. Well, there's more to it than that. They're related also in a way to derivatives, in the fact that there is an operation that is this integral sign. This integral sign is really an operation that we're performing. And sometimes we performed it on, well, always we performed it on some function with some numbers. And so when we perform it with these numbers, we end up getting some number out in the end. But sometimes when we do an integral, we get out a function instead. So we might look at a situation like this, where we have a constant as one of the limits, but a variable as the other limit. Or later on, we might look at something where we have somewhere variables or functions as both of the limits of this. Or we might, and we won't do this as much today, we might look at an integral of some function like, I don't know, 1 minus x dx, where there are no limits on it. So we need to be able to do all of those different things. And so there are different types of integrals. The integral that has limits on it, like this, or that has numerical limits for both of them, is called a definite integral. And an integral like this that doesn't have limits on it is called an indefinite integral. And if I were to do this operation, the integral operation, on a function like x squared, this result is some other function. And we're not going to worry yet about what that function is. But the most important thing for now is that you understand that when we integrate a function without limits on it, we can get some other function. Or if we integrate some function, in fact, let's just this time call it f of t dt, any random function with some variables in it, we get some other function. We don't just get a number out, but we get a function out instead. Okay. Everybody okay with that? Yeah.
Yes.
Yeah.
Okay. Cool. So, I know I wrote a 7 down here, but let's call this a 0. Let's change this to a 0 for now. So suppose I have some function. There's some function, right? Well, what this here means is the area underneath this function f of t from 0, so right here from 0, to some other number x. We'll call that x. Right? X could be 10, or x could be 1. Right? X could be any number that I want it to be. And so when I evaluate this, I get a function, some other function, that represents the area underneath this curve, f of t, from 0 to any x value I want, whether that x value is 10 or 1, and I'm just looking at this area, or perhaps that x value is 100, right? and I'm getting some value way out here with some other bigger area. Perhaps that number is -2 and I'm going the opposite direction. But I get some function that represents the area between 0 and any x value I choose underneath this specific function. Does that make sense?
Yeah.
All right. Cool. Great. That's the first part of this. Now, that's part of the first part of this. So, what we generically call this other function is capital F of x. So we might say that the integral of some function little f from any constant, so our constant was 0, to x is just capital F of x. It's just some other function that we're making up. It's just this other function. And there is a very special relationship between that function, capital F, and this other function, little f, that was inside of our integral sign. And that very important relationship is that the derivative of capital F is equal to little f of x. So the integral of little f is capital F, and the derivative of capital F is little f, which tells us that derivatives and integrals, or we sometimes call integrals antiderivatives, derivatives and antiderivatives, or derivatives and integrals, are opposite operations of each other. Does that all make a little sense?
Yes.
Okay, so that's the most important part of this first part of the fundamental theorem of calculus. Now, we're going to go back and we're going to start talking about all this again. But what I've written here is that the derivative of capital F with respect to x should be equal to the derivative with respect to x of this. And then that should come out to be our original function that we had inside the integral. So effectively, derivatives and integrals are opposite operations of each other. So doing an integral is like doing a derivative, just in reverse. So that being said, you know what's the derivative of sine function? What's the derivative of sine of x?
Cosine of x?
Cosine.
Cosine of x. Well, what is then an integral of cosine of x?
It'd be sine, right?
It should be sine of x. Okay? And so we're going to be able to use all of these rules for derivatives that we learned previously, like the derivative of sine is cosine, to tell us what the integral of cosine is. Well, it's sine. So if I was trying to figure out what the area underneath the cosine curve was, I would actually use its integral, sine x, to help me to figure that out. Does that make sense? Good or no? Yeah, everybody good or no?
Can you repeat that, please?
Okay. So since what we have up here says that the derivative, so I'm sorry, what we have up here is the integral of little f is capital F, and the derivative of capital F is little f. That means that the derivative and the integral, or you'll hear me use them interchangeably, integral and antiderivative, they're the same thing. Okay. The derivative and the integral are opposite operations of each other. So that if I know the derivative of a function sine is cosine, I know that the integral of cosine is sine. And so if I were asking you to find the area underneath the cosine curve from 0 to 2, we would be using the sine function to help us do that. And we're going to talk a little bit more about how we would use that sine function to help us do that. But it's going to help us to not have to use that limit and that summation eventually. Tomorrow, it's going to help us with that. Does that make sense?
Yeah.
Okay. Cool. All right. Now, that's going to lead us into the second part, because well, I just had it written here. I guess I could just Okay, I'm just going to rewrite it. So we had the integral of 0 to 2 of cosine x, right? And I said I needed to use sine x to deal with. So the question is, how do I deal with these zeros and these twos? We knew how to do that when it was like this limit and this summation, right? Because that became b minus a over n was our delta x, and our x sub k was a plus k times that, and we dealt with it that way. And that's how we used the zeros and twos. But the second part of the fundamental theorem of calculus is going to give us an easier way to deal with that. And it's going to say that if I know the function that I am taking the antiderivative of, right, I can take its antiderivative. So we said the antiderivative of our little function, little f, was capital F. I can evaluate this antiderivative or this integral at the upper limit, and I can evaluate it at the lower limit and find the difference between those two, and that will give me the integral of this original function that I started. So using that logic, the integral from 0 to 2 of cosine x should be equal to sine of x evaluated at 2 minus sine of x evaluated at 0. That should tell me the area underneath the cosine curve from 0 to 2. That's this whole idea of the fundamental theorem of calculus. So find a function who I know has the derivative of cosine, that's sine. So that's the integral of cosine, and then evaluate it at the upper limit and evaluate it at the lower limit and subtract them. And that should tell me the area underneath this curve. Does that make sense? That's what this second part is saying. Find the antiderivative of little f, evaluate it at the upper limit, evaluate it at the lower limit, and find the difference between them. Good or no?
Good.
Is this just something like you have to know, or is there like a reason why you can do that?
Well, there's a reason why. And it has to do with these Riemann sums that we were talking about. Let me let me just put the page in here. So we've got some function, and tell me then, if I were looking for the area between A and B of this curve f of x, right? The area of that, which we know is equal to the integral from A to B of f of x dx, right? That's what we said before. The area is the integral. Well, if I were to draw a bunch of tiny little rectangles inside of here, and I wanted to take the derivative of this, what is a derivative telling us? A derivative tells us a rate of change, doesn't it? Isn't that what a derivative does?
It's like the slope of the function.
Right, it's the slope of the function, which is the rate of change of that function, right? That's what a slope is, it's a rate of change. And in fact, it's an instantaneous rate of change at any point. And so if we wanted to take the derivative of an integral, what does that mean? That means what is the rate of change of the area, right? Because the integral represents the area, and the derivative tells us rate of change of that function. Does that make sense so far?
Yeah.
Okay, so the derivative of the integral should be indicating to us the rate of change of the area at an instant. So if each of these little rectangles is so infinitesimally thin that there's really no thickness to them at all, that the width is 0 or very, very close to 0, you know, it's 0.00000000000000001. Well, the thing that most affects the area of each of these little rectangles that we sum together within this integral is the height of each one of them, isn't it? Because this height is far bigger than 0.0000000001, right? It's far bigger than 0. And so that height is what's changing it. And so the rate of change of the area underneath this curve as we move over just the tiniest little fraction is represented by the height of this function, which is the value of f of x. Does that make sense?
Yeah, so basically like your height is the only thing that's really changing. Right.
Exactly. Yeah.
Okay.
So if we want to say the rate of change of the area of underneath this curve is just the height of this function itself. And so that's telling us that the derivative, the rate of change of the integral, the area, is the value of the height of this function, which is just f of x.
Okay, thank you.
Does that make sense?
Yeah.
Yeah, it's a little convoluted. It's very conceptual, but that's the whole idea behind why these derivatives and these integrals are opposite operations of each other. Everybody good? Everybody hanging in there so far?
Yeah, so far.
All right, good. So we've got now the derivative of the integral is the original function. So a derivative and an antiderivative, or a derivative and integral, are the inverse operations of each other. And we've got, if we want to find the integral of a function on an interval from a to b, then we just find that integral function, and we evaluated the upper limit, and we evaluated the lower limit, and we find the difference between them. Everybody on the same page that those are the sort of 2 or 3 things we've talked about so far?
Uh-huh.
All right. Wonderful. Okay. So, well, I have a blank page here. Let's get rid of that. And take a look at this problem right here. The derivative with respect to x of the integral from negative pi to x of cosine of t dt. Okay. So first off, what we need to do is we need to figure out what is the integral function of cosine of t. Now, I know we said that a minute ago, that the integral function of cosine was sine, right? Everybody remember doing that?
Yeah.
Yeah. So suppose we didn't know that that was the case already. Suppose we just didn't know what the integral function of cosine of t was. Let's just say that it is equal to capital F, because there are going to be plenty of functions that we throw in here that you might not know the integral of. So we're going to let capital F be an antiderivative or an integral of cosine t. What does just this part of it then mean using the second part of the fundamental theorem of calculus?
It's equal to cosine t.
Well, so the second part here says that we take the integral function, which is what? Capital F, right? F is our antiderivative, our integral function, and we evaluate it at.
So would it be at capital F of x plus or minus capital F of negative pi?
Exactly. So that's what just the part I boxed in blue means. And then we also have to include into this, then now we want to find the derivative of that. Good or no?
Yes.
Okay. Cool. So what is the derivative of capital F of x? What's the derivative of the antiderivative of cosine?
It's just the original function.
It's just the original function. It's just the cosine of x. What about capital F of negative pi? Well, negative pi is not a variable. Negative pi is just a number. And capital F is just a function. Hold on one second. Sorry about that. Okay, so negative pi is just a number, and capital F is just a function. So if I evaluate a function at a number, what do I get?
A number.
We just get a number. And if we take the derivative of just a number, what do we get?
That number.
No,
0.
No.
we get
Zero.
0. Yeah, we just get 0. So the derivative of the integral from a constant to x of some function is just that function back in terms of x. And that was exactly what this first part of the fundamental theorem of calculus told us. Right? The derivative of the integral from a constant to x of a function is just that function. And that's proving to us that the derivative and the antiderivative are inverse operations of each other. Good or no?
Good.
Great. All right, so what about this next one? This is the derivative of the integral from a constant to x of a function. What should we get?
That function, right?
We should just get that function in terms of this new variable. Easy enough. Or no?
Simple enough.
All right. And if we wanted to write it all out this way, we could have. We could have said capital F is antiderivative of 1 over 1 plus t squared and gotten the derivative of capital F of x minus capital F of 0. And the same thing would have happened. The derivative of capital F would have just been this, and this part would have been 0. Good or no?
Good.
All right, cool. So let's take a look at this, but slightly more difficult now. So we want to find the derivative with respect to x of this function right here. Right? So what do you think we should do? What's an antiderivative of cosine? We talked about it earlier, right? What's an antiderivative of cosine?
Sine.
Yeah, it's sine, right? So what we could do is we could write this out as we want the derivative of the antiderivative function of cosine, which is sine of x squared, minus the antiderivative function of cosine, which is sine of 1. Everybody see that that's what we could do here? Or if we didn't recognize that sine was the antiderivative of cosine, we could have just called it capital F. We could have said capital F of x squared minus capital F of 1. Either way would be fine. Good or no?
Yeah, makes sense.
So now comes the extra little added part to this. What's the derivative of the sine of x squared?
Cosine x squared.
Say that again. I couldn't hear you.
Negative
would be
2x
like-
cosine squared.
So this is a composition of two functions, right? Sine of u with u equal to x squared. So it becomes cosine of this, right? It's cosine of x squared times the derivative of x squared. It's the chain rule, right? 2x cosine x squared. And what about
Right.
this one? The derivative of sine of 1. Well, sine of 1 is just a number. So it's 0. So if this thing in my upper limit, or if I happen to have it in the lower limit, was a function rather than just a variable, we'd have to use the chain rule to find that derivative. Does that make sense to everybody?
Yeah, it makes sense.
All right. Any questions so far on anything we've done?
I'm just like a little confused. Like, wouldn't the antiderivative be like negative sine of t? Or
Well, we're not finding, this is finding a derivative of sine, not finding an antiderivative of it. Right, what's the derivative? The derivative of sine is cosine, right?
oh, okay, yeah, I see.
So if the derivative of sine is cosine, the antiderivative of cosine is sine.
Oh, all right, yeah, I understand. Thank you.
Okay, yep. Everybody good? All right, so let's do this bottom one. What should we do with the bottom one?
We can try to find the antiderivative function for e to the t squared.
All right, and that's going to be difficult for us to do. In fact, we're not going to be able to find that, but that would be a start. That would be something we'd like to be able to do, but we don't have to because we can always just make up some random function for it. So let's just call capital F and say it's an antiderivative of e to the t squared. We could do that, right? We could just make up some function because what we're going to do is we're just going to take the integral, but then take the derivative of it. So we don't actually need to know what this is for this particular problem. So what we're now looking at is a derivative with respect to x of capital F of the upper limit, using the second part of the fundamental theorem of calculus, minus capital F of 0. So does everybody see why we don't actually need to figure out, like here we found out that it was sine, but we didn't necessarily need to. Same thing here. We could try and figure out what this is, but we will really struggle to do that. So we'll just call it capital F. Because all we're about to do is take its derivative and go back to the original function.
So is it basically like taking the inverse of an inverse function?
Yeah, effectively that is what it is. They're inverse operations at each other, which means that they cancel each other out, just like taking, if you were to take the inverse of something, that would do the same thing. Yep. It's just like, adding and subtracting. If I add 2 and subtract 2, those are inverse operations. I didn't change the function or change the number, right? Or multiplication and division or square rooting and squaring. The same concept. Does that make sense?
Yeah, that makes a lot more sense now.
Okay, cool. So now I need the derivative of capital F. Well, capital F was the antiderivative of e to the t squared. So what should the derivative of capital F be? It ought to be this function I started with. And since this is capital F of x squared that we're taking the derivative of, when we take that derivative, we need to use the
Chain rule.
chain rule. So the derivative of capital F of x squared should be e to the t squared, but I need to plug in x squared for t. And I need to multiply it by the derivative of x squared, which is 2x. And then the minus capital F of 0, well, capital F is a function evaluated at a number, gives me a number. And when I take the derivative of a number, I get 0. So we end up with 2x e to the x to the 4th. Good or no?
Yes.
Any questions on that?
Wait, oh, sorry, never mind.
You're good?
Wait, could I, like, when you went from 2xe and then the other stuff, could I just keep it as 2x capital F of x squared and then go to that step?
I'm not sure what you mean. Instead of doing,
Like, would it be correct, like, still fine if I, like, when you took the derivative and then inside of the brackets, you have capital F of x squared? Could I just write, like, not in the derivative, but separately 2x f capital F of x squared?
No, because the 2x only comes in when I take the actual derivative of that.
Okay, wait, I think I get it then. Thanks.
Yep. All right, we're gonna do a couple more of these. So let's see if we can work through these. So this one's a little bit different. How is this one different from the ones we did previously?
The lower limit isn't 0.
Yeah, our lower limit's not 0, or it's not a constant either, right? Our lower limit's a variable and our upper limit is the constant. But we should be able to, and in fact, there's 2 different ways to go about this one, but we should be able to do it in the same method that we did before. Right? We don't know what the antiderivative of 3t sine t is, but we could call it capital F. Right? Say capital F is an antiderivative of 3t sine t. And we could say that this is now what? The derivative of capital F of the upper limit, which is
5
minus capital F of the lower limit, which is
x.
And so when we take the derivative, what's the derivative of capital F of 5?
Zero.
Okay. And then what's the derivative of capital F of x? If capital F is an antiderivative of this function, then
Is it just the original function?
it's just the original function, 3x sine x. So our final answer here should be negative 3x sine x. Good or no?
Yeah.
Good.
All right. Now, there was another way we could have done this, and I'm going to jump ahead for just a second. We're going to talk about some rules for integrals in a bit. I want to talk about one of them right now. And I'll give you a chance to come back and write all these rules down in a little bit. But this rule is very important to integrals. If I have the integral of a function from a to b, I can flip the limits of integration by putting a negative sign out in front of it. Okay, this is a very important rule. And if I were to think about that over here and just originally flipped these limits to 5 and x, I could have made this a negative out in front. And then it would look very much the same as all the other ones we did before, right? Like these ones, right? Where I just had the derivative of the integral from a constant to x of a function just came out to be that function, or the derivative of a function or of an integral from a constant to x of a function was just the function. Well, it would be the same thing here, except I'd have a negative sign out in front, and then I'd be looking for the derivative of the integral from a constant to x of a function. It would just be negative because of the negative sign, 3x sine x. Good or no? Good, not good, maybe good.
Maybe good.
I'm good.
Okay. Any questions?
If I'm reading the rules right, like you could do like the 3t sine of t, like you could put the 3t in front too, right?
Outside the integral sign?
Yeah. Or wait, would it only be the 3?
Yeah, based on this rule that I've got here at the top that we will talk about in a bit, yeah, you can move the constant out. You can put the 3 out, but not the t.
Oh, okay. That makes sense.
Okay. Cool. All right. Let's do one more of these. What should we do to start?
Set it up with the capital F's.
All right, so let's call capital F an antiderivative of 1 over 2 plus e to the t. And we can set this up then now as a derivative, because that's what we're asked to do, is find the derivative of capital F of what?
X squared.
Okay, minus
Capital F 2x.
capital F of 2x. Good. Everybody good there?
Yep.
All right. What's the derivative of capital F of x squared? Using the chain rule, right? Because this is now a function evaluated at another function. It's a function within a function. it should be the derivative of capital F. What's the derivative of just, the function capital F? It's this, right? Go ahead.
Yeah. Would it be just 2x over 2 plus e to the power of x squared?
It's exactly what it would be. So it's the derivative of x squared, 2x, times this, evaluated at x squared, which is 1 over 2 plus e to the x squared. But this time, the second piece of it isn't a constant, right? So we have to just do this derivative again. It's now the derivative of 2x, using the chain rule is 2, over 2 plus e to the t, which is this value at 2x. And that would be our answer. 2x over 2 plus e to the x squared minus 2 over 2 plus e to the 2x. Good or no?
Yeah, good.
All right. Wonderful. Anybody have any questions before we move into all those other rules and finish up? We're actually going to finish up a little early. Somehow. I'm not sure how, because first period we went over.
I just had a quick question about the one before this one.
Mhm.
Why wasn't the answer the derivative of 3t or 3x sine x?
Because we're taking the derivative of the integral of this function. And so the antiderivative, the integral part of it, is capital F. And then we take the derivative of capital F to come back to the original function.
Oh, okay.
Yeah, because we're canceling out this integral with this derivative.
Okay.
Does that make sense?
Yeah. Thank you.
Mhm. Any other questions on any of this? Because that's about all we're really going to do with these problems that involve specifically the fundamental theorem of calculus. All right. Not everything we do will be a derivative of an integral. Most of the time, what we're going to do is just an integral. And most of the time, we're not going to have variables in the upper and lower limit, or even in either the upper or the lower limit of our integrals. This is just what we've been doing today is just one very specific thing that that is normally taught in calculus classes, as it's kind of like a proof of why these derivatives and antiderivatives cancel each other out. They will ask you to do something like one of the problems that we've done today, probably once or twice on the AP test. But 99% of what we're going to do with integrals, we will either have an integral of some function with no limits on it, which we call an indefinite integral, or we will have an integral of some function with some numeric limits on it, which we call a definite integral. So 99% of what we're going to be doing will be these two things. Only the little 1% is this fundamental theorem of calculus with functions in my limits as I'm trying to integrate and take derivatives of it to just sort of see how these integrals work. So we need to know how to do all of this stuff, but it is not the majority of what we're going to be talking about this unit. Okay, so that's good news because this stuff gets a little convoluted sometimes. Once you figure this stuff out, it's really easy, but sometimes it's pretty hard to grasp. So the majority of what we're going to be doing is these two things. And this one we already know how to deal with, at least in one way, right? By doing the limit and the summation. And we're tomorrow going to develop a new way to deal with both of these. It's going to make life a lot easier. But before we do that, we're going to talk about just some of the rules of integration and how functions can be sort of combined together or separated apart or altered within an integral, because that's very important to what we will be doing the rest of this unit. So any questions on what we've done so far before we kind of change gears for the last 5 minutes here? That's gonna probably take us. Maybe 10.
Would what we did today ever be kind of like, is it always like directly stated when to use it, or is it kind of like in another time that you should just know that this is when you use it?
Yeah, you just kind of need to know. It won't directly state. It might, but it probably won't directly state use the fundamental theorem of calculus to do this. Yeah, you just
Okay.
need to recognize that.
But it won't
when
be
it
in
asks
kind of
for
like
the
a
derivative of an integral. This is the process you want to take.
But it won't be like in a word problem kind of thing, and then you have to know just to use this to be able to find something.
There will be some instances where it could show up in a word problem,
Okay.
but we won't see any of those until we've covered all of the rest of the integration stuff, because it's usually combined in with other stuff, and you gotta sort of separate it out.
Okay.
What it's called is they end up being called accumulator functions. So you don't need to worry about what that is yet, because we'll talk that in the future. But,
Okay.
all right. So let's take a look at these rules that we started talking about a minute ago. First one was that we could flip the limits of the integral and put a negative out in front of it. We can still do that. We can always do that. It never changes. We can always do that. Other things that we can do with our integrals is if we have a constant times a function, we can take that constant and pull it out in front of the integral sign. Okay. We can, so if I had, for example, somebody was mentioning it back here with the 3t sine t. If I'd wanted to, I could have pulled that 3 outside of the integral and then dealt with just t sine t instead of 3t sine t. Okay. Just like we did with limits, and just like we've done with derivatives, and just like we talked about doing with summations, right? We can pull a constant out of any of those things. Next thing is, if I have an integral from a to b of one function plus another function, so like, let's say x squared plus x, if I wanted to, I could separate that into the integral of x squared plus the integral of x, or I could do it with a minus also. Good? Okay. And then the last two things down here, one, this integral from a to a of f of x dx is 0. That one should be really easy to grasp, I hope. Here's a. An integral represents an area underneath a curve. So I'm looking at the area underneath f. Well, what's the area between here and here? I didn't go anywhere, right? So what's that area?
Just
0.
0.
It's 0. There is no area, right? And there's no space. There's no, there's nothing underneath this curve from here to here because I didn't go anywhere. So anytime you integrate from 2 to 2, it's 0. Or from 7 to 7, it's 0. From -3 to -3, it's 0. Okay. And then lastly, this one down here, if we think about it in terms of area, again, I think it's very helpful. Here's a, here's b, and here's c. The integral from a to b of a function, that's this, right? And the integral from b to c of a function, well, that's this. If I want the integral from a to c, that ought to be the integral from a to b plus the integral from b to c. Everybody okay with that?
Yep.
Okay. And likewise, if I wanted to, if I knew the integral from a to c, and I knew the integral from a to b, I could subtract a to c minus a to b, and that would give me b to c. So you can rearrange this in any way you want to. Good or no?
Yep.
Okay. And something that ends up being very important, not for us necessarily so much, but in Calc 2 and some differential equations classes when you get into higher math, these integrals can be treated as one full entity, and I can perform algebraic operations within an equation that involves integrals. So like I could subtract this over to this side and have a true statement, just kind of like what we just talked about. All right, so what we're going to do now is one last thing. We're going to use those rules that we just talked about and some given values of integrals of random generic functions to answer these 5 questions, and then we'll be done for the day. So we've got 2 continuous functions, f and g, continuous for all real numbers, and we want to find these 5 integrals. So number 1, what's the integral from 2 to 2 of g of x dx?
0.
0, right? Because we're going from 2 to 2. We're not going anywhere. There's no area underneath the function on that interval, so it's 0. Good. What rule will we use for the integral from 5 to 1 of g of x?
The one where you can flip the limits and make it negative.
Exactly. So this should be equal to the integral, the opposite of the integral from 1 to 5 of g of x, which is the opposite of 8. Good?
Yep.
What rule can I use for the next one?
First one where you multiply it by a coefficient.
Okay, take that constant, that coefficient out. This is 3 times the integral from 1 to 2 of f of x dx. And we know what the integral from 1 to 2 is. It was given to us as -4. So this just comes out to be 3 times -4, or -12. Good?
Good.
Okay. What about the integral from 2 to 5 of f of x?
You can flip that first one and then use the last rule.
Okay, so we don't need to flip it, but we are going to use that last rule. Right, we're just going to use that last rule with some subtraction. If I have 1 to 5, and I also have 1 to 2, but I want 2 to 5, I need to take the full 1 to 5, and I need to knock off 1 to 2, right? Does that make sense to everyone? Yeah. And so what's the integral from 1 to 5 of f? It's 6. And the integral from 1 to 2 of f is -4, so it's 6 minus -4, or 10. Good or no? And what about the last one? We can separate that into 2 separate integrals. The integral from 1 to 5 of f of x minus the integral from 1 to 5 of g of x, which ought to be 6 minus 8, or -2. Good or no?
Good.
Cool. That's it for today. Any questions on anything we did today?
So isn't a definite integral always like a constant?
Yes, a definite integral will always come out to be a number. Yep. Will always come out to be a constant. Yep.
Okay.
All right.